guys, welcome back to my YouTube channel.
Hi guys, my name is John and these are my friends, Sze Liz and Young.
And we're from class V6.
Today we're going to talk about DC generators.
Oh, gonna sit down. Hey guys, I just dropped down from the portal up there.
Hello there, my name is John and today I'm gonna explain about what is a DC generator. So basically, the DC generator is made out of an armature coil, two permanent magnets, a commutator, carbon brush, and most importantly, the load. The load is basically anything that consumes the electricity generator, like the fan, light bulb, or something huge, like the entire resident area. So basically, a DC generator is very useful since it can turn mechanical energy into electrical energy. How it works is basically the turning of the armature coil between the magnet with external force like the wind and induces EMF. Easy. Examples of things that uses a DC generator are the windmill, water turbine, and more. This cowboy Young is gonna explain how the DC generator produces a steady DC output.
Alright, hi everyone, my name is Young and today I'm going to explain about how a DC generator produces a steady DC output. But first of all, let's look at how a DC generator works before we move on to before I explain how a DC generator produces the DC output. This is sounds like a fundamental part of my presentation. So let's look. So here's the story. So here I created a storyline on how does a DC generator works, and this is the first part of my storyline. So first of all, voltage is induced in coils by the rate of change of the magnetic field through the coils as the machine rotates. So why is it so? So because this induced voltage is inherently alternating in form since the coil flux increase and then later it decreases again with a zero average value. Now notice the word zero average value. So zero average value basically just means that there's no average value of a complete cycle, because remember DC generators, the graph is always above the x-axis. It doesn't change. It is not a sine graph like an AC generator. Alright. So this is my next part, my storyline. So the field is then produced by the direct current in field coils or by permanent magnets on the stator. Then the commutator connects the rotor coil to the stationary output terminals through carbon brushes. Now the word rotor coil might be something new to you all. So let me explain what is rotor coil. Rotor coil just basically is a mechanical device consisting of the stationary part of a motor or generator in or around which the rotor revolves, So after this, this commutator reverses the connections at the two instants in each rotation when the rate of change of flux in the coil is zero. For instance, when the enclosed flux is maximum or minimum. Alright, it's positive, negative. So this is my next part, my storyline. So the output voltage is then unidirectional, but is pulsating for the simple case of one rotor coil. Okay, unidirectional basically just means that it's going at one direction only. It's not going at multiple directions. Alright, so this is a very important concept. So then each coil is then connected to a segment on a multi-bar commutator. Okay, later the output voltage consists of the sum, and then the output voltage consists of the sum, right? Consists of the sum of the induced voltage in a number of individual coils displayed around half the periphery. Okay, periphery might be something very new to all of you. So periphery just basically means that the outward bounds of something as it is distinguished from its internal regions or center. It basically means that if you imagine it as a circle, it's just the perimeter of the circle. That is called periphery. Yeah. Alright, here's my next slide. My next part of my storyline. Now, the magnitude of the output voltage is then approximately constant, containing just only a small ripple. Okay, why it just contains small ripple? This is because the voltage magnitude is proportional to the rotor speed and the magnetic flux. To be exact, is directly proportional. Alright. So at the end, the control of the output voltage is provided by control of the direct current in the view. Alright. So this is now I'm going back into the question. How this DC generator produces a steady DC output. Okay, let's look into it, yeah. Alright, first of all, the generator is referred to shunt excited. Okay, what is shunt excited? Shunt excited right here. Alright, shunt excited basically just means that it's a type of direct DC generator on the basis of source of field current. Alright, you can refer to your DC generator diagram to have more information. It just basically means that the basis of source. Alright. Okay, now it has the later, and then it has the advantage of requiring no intermittent electrical supply. This is one of the advantages of DC generators. So because it doesn't requires independent electrical supply, so it also means that it doesn't require, so it means that it also can produce steady output. Alright, this is the one of the best parts of DC generators. Next, residual magnetic flux in the iron poles produces a small generated voltage as the machine is brought up to speed. Alright, so the consequences are it causes the field current that increases the flux. Alright, it increases flux and then it turns the generated voltage. And in turn, the generated voltage is measured in that way. Alright, so later the voltage then builds up until saturation in the iron limits the voltage produces. So those who taking chemistry, you should be familiar of the word saturation here. Okay, saturation just means that the degree of extent to which something is dissolved or absorbed. For here is absorb, yeah, absorb compared with the maximum possible until the iron limit. So this is basically what it means lah. Alright, so it's also usually expressed in percentage. The unit is also usually in percentage unit. Alright, so at the end, the stable value of the generated voltage can be adjusted over a limited range by just adjusting the value of a resistor placed in series with the field coil. Alright, so with that I've finished my presentation. So I will let Jason to continue with his part, and that's it. See you in Jason's part. Thank you.
Okay, 2, 1, go.
Good morning, guys. Today I'll be giving you a better explanation on how Faraday's law and Lenz's law apply to the flux over time graph and the EMF over time graph. So here I have two permanent magnets. The magnetic field is moving across from the North Pole to the South Pole. We have an armature coil in the middle with the current flowing in the clockwise direction. Here I have three graphs: the flux over time graph, the change in flux over time graph, and the EMF over time graph. So at the beginning, the armature coil is placed parallel to the magnetic field, and the normal is perpendicular to the magnetic field. And according to this formula, the area enclosed by the armature coil is at its minimum, which means that the flux, since the area is at its minimum, the flux will also be at its minimum. This is why the graph will start from 0. As the armature coil moves in a 90-degree rotation, the area enclosed by the magnetic field increases to its peak. And as it continues to rotate into a full circle, the area enclosed by the magnetic field, by the armature coil, will continue to increase and decrease. And this will be how the magnetic flux over time graph will look like. Okay. Next, I'm going to talk about the change in flux over time graph. And for this graph to work, we will need Faraday's law's formula, which is EMF equal to the change of flux over the change of time. This is also the gradient of the flux over time graph. So, as the flux starts from 0, the gradient is at its maximum positive value. Therefore, the change in graph will look like
The change in flux.
the change in flux over time will be at its maximum positive value. As the graph goes up, the gradient will slowly reduce to 0. Therefore, the change in flux will be at its 0 point. As the graph goes down, the gradient will increase to its highest but in a negative value. Therefore, the change in flux will go below the x-axis. And as the flux goes up again, the gradient will increase and reach its maximum value. Therefore, the change in flux will be at its maximum value. And this will be how the change in flux over time graph will look like. Now, according to Lenz's law, EMF will be equals to the negative of the change in flux over the change in time.
Hey, my name
which
is
means it is the
Businessman,
negative
and
of the
today
gradient
I
of
have
flux
brought
over
with
time
me
graph.
Michael
So all we
Faraday
have to
and
do
Emil
is
Lenz
take the
from the
change in
past.
flux over time graph
They are going
and
to
put it
be the
into a
one
negative value.
explaining on how
So at the point
the
where the
portal
change in
works
flux is
based
at its
off
positive,
of their
the
laws,
EMF over time
Faraday's
graph
law
will be
and
negative.
Lenz's law.
And
Oh,
it goes
hello
on for
there.
the entire graph, and this
My
will be
name is
how the
Michael
EMF over
Faraday,
time graph
and
look
today
like.
I will be explaining about
The
my
end.
law, Faraday's law, obviously, and how it is related to the portal which Emmett fell from. So basically, DC generators produce electrical power based off of my law, which is the Faraday's law of electromagnetic induction. Since it is my law, I am the one stating that when a conductor moves in magnetic fields, in which this case the conductor being a pair of scissors, it cuts magnetic lines of force. Cutting through the magnetic lines of force will then induce an electromagnetic force, also known as EMF, in the conductor. It is also a law stating that when the magnetic flux linking a circuit changes, an electromagnetic force is induced in the circuit. Thank you very much, Mr. Faraday, for that enlightenment of your law. Now, let us please welcome Mr. Lenz to explain his law, Lenz's law. An electromagnetic force induced in the circuit is actually proportional to the rate of change of flux linkage. Thank you very much, Mr. Lenz, for explaining your law.